Freddie just asked about this question. I think it gives some nice insights. So first of all, it's a differential equation, a normal one. In other words, it's not coupled, which means it has an associated slope field rather than phase portrait. And then you should know that on the syllabus for differential equations, you might be asked to solve it by hand, in which case you would separate and integrate. But that's not this question. Number one, because that's not possible by hand. So then there's two more possibilities for what they're going to ask you about. They're going to either ask you about slope fields, or they're going to ask you to do Euler. And Euler is a way of solving a differential equation numerically, at least for a short distance. So this is a slope field question, and they give us this, and they give us the slope field. And there's the slope field for that differential equation. And you should be thinking, if they just give me a starting point, I will just follow the flow round. So you're looking for that in the question. But in this question, they start with this quite difficult to interpret question. Some of the solutions to the differential equation have a local maximum point and a local minimum. Let's just first of all investigate that. What does that mean? Well, let's imagine I started here, there. Then I would just sit in my rubber dinghy and follow the flow. It goes down there, and it would go around there. That doesn't have a minimum and a maximum. It's only got a maximum. But if I started, let's say, here, then I can follow the flow, and it'll look something like that. And you should extend it to the correct domain for the question, and I would make sure I didn't go past the 3. So some of the solutions to this differential equation have a local maximum and a local minimum. Well, I just drew one of those. Write down an equation on the curve on which all of these maxima and minimum points are. So what Freddie and I did was said, well, let's just have a look at some of them. Where are these maximum points? Well, clearly there's a flat point there. There's one there. I'm just searching through for flat points. There's clearly others. There's got to be one around. Oh, there's one maybe. It looks very flat around here, and it's clearly flat around there maybe. And so there's a lot of places. So what's it referring to when it's saying write down the equation of the curve on which all these maximum and minimum points lie? And it's as simple as saying, what is a maximum point and a minimum point? It's a place where the gradient is 0. So I'm going to just take that gradient and put it equal to 0. Let's just put that equals to 0. Just put a 0 there. 0 equals x squared plus y over 2. Rearrange that. Y equals negative 2x squared. So it must be true that everywhere on this slope field, y equals negative 2x squared must be true. And you can see that Freddie and I were on the way to plotting that point by point. Negative 2x squared is an unhappy quadratic that looks something like this. So I'm drawing with the mouse. And so that will definitely go through every maximum minimum point. Really nice. The next part said, much more normal. The solution to the differential equation that passes through 0, minus 2 has both a maximum and a minimum. On the slope field, sketch it. So I put my starting point on, and then with as much accuracy as I can, and you don't need to go mad on this, I just follow the flow. So I don't know, about there. And there'll be quite a lot of leeway given for a sensible sketch. And that's a solution to this, in the sense that we know what it looks like. We don't know what its equation is. because we can't solve this analytically. We can't separate, and therefore we can't integrate, and therefore we can't actually know what the equation of this curve is. Nice question.